All right. Well, I hope you guys had a nice weekend. And 4 days have gone by, and now we have the class again. I personally don't like classes when when there's a long period of time between classes. With this class, I like Monday, Wednesday, Friday classes. When they still had Monday, Wednesday, Friday classes.
You said in your lecture in 2010 that you hated Friday classes.
That's Friday only classes.
Yes.
Yeah, Friday only classes are a whole different thing because you don't meet the entire class for 1 week.
Yeah.
So so 6 days later, the class meets again and completely forgets what
That's
I
where
talked
you
about
have
the class before.
Your YouTube videos are divided in 0 to 5 increments. I used it on the homework. I had to go back and look at it. So
Wow, I'm impressed somebody actually dig up all the old videos.
I've been back for 4 semesters.
Okay, the first thing I want to do is just point out something that you don't have to do, but it is something that you can do if you want to. There's a link here, that most of you do not see because you're not the creator of this particular course, but you can still get to it as a guest. So if you remember the URL, or I can just post the URL on our website, so you can actually get to this part here. This is a little website that I created for Career GPS. Does anyone know what is Career GPS? Nobody. Okay, Career GPS is an exhibition at Cal Expo. It's going to be the 25th and 26th this month, and that's why I'll be missing class on that Thursday, on the 26th. We won't have classes on that day because I'll be over at Cal Expo. But there will be about 5,000 or 6,000 middle school and high school students walking through the exhibition on that day. And the purpose of the show, or the purpose of the exhibition, is to expose students, middle school and high school students, to different types of careers. So they can start to think about, okay, what do I want to do when I'm done with middle school or high school? And then they can start to do the planning, what classes should I take, and so on and so forth. And that's the whole point of Career GPS. But I'm thinking that this may be helpful, or certain links of this can still be helpful to you. Here's a little link to Holland Code Assessment, okay? So I'm going to go there. You guys can do it on your own, okay? It's interesting. It is a quiz, okay? Holland Code is basically, if you click this link here, it is a code that kind of help identify what type of a person you are. Okay, realistic, investigative, artistic, social, enterprising, and conventional. Those are the 6 individual types. Now, you don't have to fall into one category only. Some people can fall into multiple categories at the same time. Okay, so by answering the questions of this quiz here, it will tell you something. It will give you suggestions. Okay, but the suggestions are specific to Rogue Community College, and so it will recommend programs from that particular college. But at the same time, a lot of those programs, we have it on this campus as well, and it'll help you kind of identify, okay, am I in a major that is suitable for myself? Okay, sometimes, we may or may not, get into a program that is, suitable for ourselves, because sometimes, we have, like uncles or other people telling us, oh, you should study this, okay? Well, maybe it's a good fit, maybe it's not a good fit. So, it's a fun thing for you guys to do. Obviously, it's not mandatory. I'm not going to grade, the result from this, thing here. You can also type in, you can pretend to be somebody else and type in, answer these quizzes and see whether what you think that person is actually what that person is. So it's kind of interesting. I think with me, it's actually pretty accurate. It recommended all the computer science courses, which is good, right? It's a confidence builder for you guys. It's like, okay, so my professor is actually suitable to study computer science. Instead of no, he should have become an artist or something. That probably won't be very, it won't inspire confidence. Let's just put it that way.
We have evidence to prove that's wrong too.
Huh?
We have evidence to prove that's wrong too.
What?
Your drawings when
My
you
drawing, my pictures. All right, so this is where we are. We really need to get started with pre and post conditions. But before we get there, I just want to see what kind of questions you guys might have. For those of you who have yet started with this homework assignment, I cannot answer the actual questions, but I can give you maybe
You can answer similar questions, right?
I can answer questions with more questions. Yes.
So I have a question.
Yeah.
In the last 4 semesters, you have not used else if and else if within a while and while condition. I went back yesterday in an extensive search. You will find a loop within a loop, but you won't find an else or an else if. And I was
Okay.
hoping to kind of find a model to be able to go off of. Now within our nested statements, we have a while and a while. So we have a loop within a loop.
You
Not
mean
on this
in the
example,
notes,
but
in our
within our
notes,
notes,
right.
within our lecture.
Mhm.
So in reviewing that, and then going back to conditional statements in general, I was getting a bit confused. We have a while and end while loop, it seems. And I know that you can't answer.
Okay, so let me ask you a question. Okay, so if I just focus, okay, forget about this entire program. If I just focus on this part here, and I tell you that x has a value of, I don't know, say x has a value of 11 at this point, okay? Do we know the behavior of this code knowing that x has a value of 11?
Yes.
Very good.
Do we?
Yes.
Yeah, that was it.
Okay, so once you know the behavior of this code within only the context of line 6 to line 10, then let's push it one more, okay? Because now if I push it to this level, do we know the behavior of this kind of slightly more complex code knowing that x has a value of 11?
Yes.
Okay, so now we push it one more level and say, if we look at the entire loop, okay, at this point, let's say we're on line 2, x has a value of 11. Do we know what this code is supposed to do?
Yes.
Well, there you go. You just answered the question, right? In other words, what I put inside the loop doesn't matter, because whether the if then else or the else if conditional statement is inside the loop or outside the loop doesn't matter. It doesn't change the behavior of that particular statement. So that can be inside, okay. So right now we have line 6 to line 10, being inside the else branch of another conditional statement. But whether it is inside another conditional statement or not doesn't change the behavior of that, if else if the multi-branch conditional statement. Okay. The best way to approach this particular homework assignment, if you think, okay, I'm not quite sure whether I'm getting it or not. If you think, okay, no problem, I think I'm getting it, then you don't have to go through this step. But if you think, I'm not 100% sure I'm getting what this code is supposed to do, the best way is to start drawing a picture. Because once you draw a picture, you have to think about how am I going to draw that picture, okay? And remember what I did in class to draw the picture? I draw the outermost layer first, and then I get into one more level, and then I get in one more level, okay? And that's exactly how you should draw the picture, is to not to try to draw it from line 1 to line 12, but to draw it in in layers. So if I were to draw a picture about this code, I would draw, this is an easy one, right? So there are 2 statements at the top level. We have line 1 by itself as one statement, but we also have line 2 to line 12 as a loop as another statement, okay? So you draw the shape of a loop, from line 12 to, from line 2 to line 12. You draw the shape of a pre-checking loop. You stuff it with the condition, so you know which way to go when it's false, which way to go when it's true, and what the condition is. So that's the shell of a loop. Once you draw the shell of a loop, then you leave a big block to specify what to do on a per iteration basis. That block is going to correspond to line 3 to line 11, okay? So when you're drawing the picture corresponding to line 3 to line 11, Whether this is all by itself outside or whether it is inside the loop, doesn't matter. It is still the same shape, it still has the same logic. Okay? So when you draw a picture of line 3 to line 11, what do you draw? You draw a conditional statement, right? You come in, there's a split, you have a condition to evaluate. On one side, you have what to do when the condition is true. On the other side, you have what to do when the condition is false. And then the two branches would merge and then continue execution, right? So when on the side that is true, you have one little thing to do. On the side that is false, you have a little more to do, okay? But it doesn't matter because when your focus is the conditional statement starting on line 3, you only have to know it's a conditional statement, it has two branches, this is the condition. Yep, go ahead.
Once you get to line 4 on your first iteration, does it hit the end if and go back to line 2? Start again?
Once you are done with line 4, then you're done with one side of the conditional statement. So now the question is, do you have anything else to do in the loop, in the conditional statement first? Okay, so let's say we are on line 4 right now. The question now is, I'm done with this statement. What is left to do in this then branch? Is there anything left on this then branch?
No.
No. Okay, so the then branch is all done. So what do you do when the then branch of a conditional statement is done? You get out of the conditional statement,
And you
right?
go back to the while loop, correct?
Well, exactly. In this case, there's nothing after the end of the conditional statement, so you have no choice but to go back to line 2 to continue execution. Okay? So try to draw a picture, because in the process of drawing that picture, you will probably get a better understanding of what it means to have a statement nested inside another statement. Okay. Did I answer?
Yes.
Okay. Very good.
I'm open.
Any other questions? Go ahead.
This is somewhat irrelevant. I was just wondering if X had a value that was greater than 20, would you just bypass this entire?
If X starts with a value that is greater than or equal to 20 when you are on line 2, then you look at the logic, because you still have the branch. You have to follow. Then you have to decide, is the condition true or false? If it is false, you always follow the false branch. Okay, wherever that leads you. Okay, but you have to know. You should know where it leads you when the condition is false. Yep.
So if it is greater than 20, then you just do line 2 and you'd say that X is less than 20 is false, and then you just go those.
Yep. Yep. Yeah, if I change line 1 to 20 instead of 0, that's exactly the behavior of the code. Yep. All right. Very good. All right. Well, this is but these questions really prompted me to kind of think and say, well, what if in this class I'm not using pseudocode? What if in this class I'm using C++ or Visual Basic, and I give you this code and ask you, okay, what is this program going to do? Most people would just type it in Visual Basic, hit that green button that says run, and say, okay, I'm done. Check out the value of X. After the entire code is done, and turn it in as my homework submission, without necessarily understanding what it means to have a construct like this. And that's why I'm using pseudocode and not using a particular programming language. Yep, go ahead.
Do you want and if lines in the trace?
No, the end if, and the end while, those lines, you should not be traced. The else lines should not be traced, because the only purposes of, line 5, line 10, line 11, and line 12, those are all just markers. They're only there to say, this is the end of this, or this is a separator between this and that, okay? So it is helpful to separate different parts of a program, but in terms of execution, those particular lines do not do a single thing, and therefore we don't trace it in a trace. Okay. It's kind of like, we don't say out the punctuations in conversations, right? I don't say, oh, this is the end of a sentence, period.
Okay.
It's kind of like that, because it helps when you're reading it, but it doesn't help as much when you're listening to it. Yep.
When we're doing our homework and we're doing the trace, so we'll go like 1, 2, 3, 4, and then on the trace, the next one's 2, and then just kind of keep
Yep,
doing it.
that sounds about right. Yep. That's all I can say. Sounds
Yeah.
about right. Okay, so any other questions about the homework assignment before we kind of move on to pre and post conditions?
No. But I will add that keeping your old semesters up does
Yeah.
help.
That's help. Okay,
Yeah.
no, that's good. But Google has not complained yet, because I probably have a terabyte of stuff on on YouTube at this point, and nobody is complaining. Yep.
I'm looking for your videos online, and I can't find them.
Okay, so write this down because otherwise it'll be a chicken and egg kind of issue. So you go to YouTube, you go to some props. So look up some props. Click the channel, and then once you get to the channel, you click videos, and that will list all the video clips in a reverse order. So the most recently uploaded video will be listed first. Okay, so if you're looking for something in the past, you have to kind of click on the next page. I don't think I have rolled over anything to the next page, because you can see that the beginning of this entire semester is over here 3 weeks ago. So we are still on the first page. If later on in the semester it is over to the next page, you can click load more, and that will show you more video clips. Okay, is that okay? So look for some props and then click videos on that page. All right, very good. Let's go ahead and get started with pre and post conditions. Now, pre and post conditions is kind of an interesting chapter, so to speak, because the first slide starts with a question of why do we have to do all this stuff? I mean, this is all crazy stuff. I signed up for a programming class, and why are we talking about math? Okay, because a lot of this is really just math. Do you guys have any questions back there? No? Okay. So here's the question, to you guys, why do we need to understand math when we just want to learn how to do programming and coding?
Order of operations is important.
Order of operations, okay, that's one. Yep.
Well, I mean, when you're programming, you're telling the computer what to do, but all that the computer can do is math, basically. Like it's languages with numbers. And
Pretty much. Yep. Down at the very core of your processors, and I don't care how fancy your processor is the processor can only do certain things, like it can move things around. Okay, so it can move certain content from one memory location to another memory location. That's pretty easy to do. It can add numbers, it can subtract numbers, it can do multiplication. When you have floating point units, it can also do sine, cosine, all the math functions, okay, in a very quick, in a short amount of time. Very efficient. It can do comparison, because comparison, after all, is really a subtraction, okay? It can also do a branch, okay, kind of like our conditional statement, but in a much more primitive way. But you can just understand it as, oh, okay, it can look at the result of a comparison and go one way or the other way, depending on the result of the comparison. And guess what? That's it. That is all that your processor can do. It doesn't matter whether you have an old processor, new processor, an ARM processor in a cell phone, or an i7 processor in a desktop. That is all that it can do. So how can these really primitive, small building blocks be able to do all the fancy stuff that we can see that computers can do today? It's all about how to put things together, right? Okay. But as far as you are concerned, why are you learning math? To answer that question, I think the ultimate question you really have to ask is, how am I going to be a valuable employee, so when the company has to downsize, I will not be on the list of people to be basically getting the pink slip? Okay, I think that's a fairly realistic way of looking at things. Okay, there's nothing idealistic about it. There's nothing that is abstract about it. Do you have a job or not? Do you want to keep your job or not? That really is the question. Okay. All right, so let's think about what it takes to be a programmer. Okay, the first thing I can do is to look at, go to Amazon and take a look at books, right? So I'll take a look at very typical things like PHP programming, and then you have all kinds of PHP programming books. You have beginning PHP, beginning PHP 5.3, and these are all pretty good books. So let's go look for some not so good books. I guess they're not popular. That's why they're not popping up early. PHP for Dummies. There we go. Okay. So now we have books intended for well, okay, they say it's PHP, MySQL, JavaScript, and HTML5 for Dummies. Okay, those are really big topics. If you really want to be an expert in PHP, you cannot get it done in one single book. If you want to be an expert in SQL in general, that's like a whole 4-unit course in a 4-year university. Okay, just to understand queries and how to get all the tables to link, all the different types of join operations and whatnot. JavaScript is not that simple. There's a lot of stuff you have to understand object-oriented programming before you even start with JavaScript. HTML5, even though it seems pretty easy, HTML5 has a lot of addition on top of HTML4 that makes it unique. Okay, so you look at this book here, and how many pages is this book? Let's take a look. Take a closer look. Find out how many pages it has.
Look inside.
Huh?
Maybe look inside.
Look inside.
Yeah,
Where?
think it's a book.
You click on the book and said look inside.
Here we go.
Table of contents.
Keep going down.
Nice. 600 something pages. Okay. I think that's way too short, to cover all the material, all the content correctly. So if someone claims that, oh, I now know how to do PHP, JavaScript, HTML5, and MySQL, just give me a project, give me a web project, I can do it. Okay? How do you think that person is going to do it? Copy and pasting code from the CD-ROM, right? I'm pretty sure it comes with the CD-ROM. Okay, so that's one way to write programs. But what do you think this person is going to run up to as far as, what situation will basically put this person in a difficult situation? Security, exactly. Or troubleshooting. What if the code in the CD-ROM has a bug? That doesn't show all the time, and that's why it's still there, because the author could not catch it, in the first time. Do you think a person reading this book, without all the other material, can figure out what that bug is and fix it?
Nope.
Probably not. Okay, so troubleshooting is a very important aspect of becoming a programmer. Okay, you have to be able to say, what if something is not right? What if this program does not behave correctly? Can I figure out what is wrong with it and fix it? Okay, I think to me that really separates a group of programmers from the rest, and basically say these guys are good at logic and troubleshooting. And if I have to choose, if I have to let go of people, I would choose to keep people who can troubleshoot, rather than people who can just copy and paste code from another source. Okay, so this chapter in our text here in our class is really about troubleshooting and really understanding and looking at the logic of your program from a rigorous mathematical point of view, instead of, oh, I know how to trace the code. Well, knowing how to trace the code doesn't help a lot when you want to debug a program. And let me show you why. I think I might have shown you this picture before, but I'll show it again. Let's say this entire circle here represents all the possible input to a particular algorithm. Okay?
It's a good circle.
It's a pretty small circle.
Nice circle.
In some cases, this circle is infinitely large, okay? Because there's no way for you to actually come up with all the possible test cases. That's just infinite, okay? So my red pen is going to indicate the cases where a particular algorithm will behave incorrectly, okay? Okay, let's make it more fair. Fine. Okay, so these are the cases where this particular algorithm. This is the input in potential cases of input into an algorithm, and these are the red dots represent test cases where the flaw of the algorithm will show up. Are we doing okay so far? When you are using the trace technique to see whether a program is doing it correctly or not, you're basically standing facing in this direction, and you're throwing dots backwards, and see whether the dots will hit something that is red or not. Okay, but you don't know even where the red dots are. Remember, the red dots are the known cases that will break the algorithm. If you had known where the red dots are, you would not be throwing the darts, would you? So that means the red dots won't even reveal themselves until it is hit by a dart. So this entire thing has no mark whatsoever when you're throwing the darts backwards. Okay? If I throw 20 darts backwards, what are the chances that it will hit something that is actually red? It is slim. Okay? Remember, this is an over-exaggeration because in reality, the green area is much larger and the red dots are much more sparsely populated. Okay? So that's what we are dealing with when we are trying to verify a program, when we're trying to say, oh, I know this program is going to be correct, or I know this algorithm is going to be correct. Are we doing okay so far with this analogy? Okay? And that's where math comes in handy. Okay? What do you do in a math class? Let's say in algebra. Okay? So let's say in algebra we do something. I'm trying to think of something that you typically have to prove in an algebra class. Can someone give me a suggestion? Because I'm prove certain things. Okay, I have one. Okay, prove that. How about something even easier? Okay, x divided by 2x is 1/2 for all possible values of x that is different from 0. Okay, because when x is 0, you have 0 divided by 0, and that's not defined. That's undefined. Okay, so I want someone to prove this to me. Okay, you guys will go, oh, that's pretty easy to do. We just use algebra and say x divided by x is 1, so the whole thing becomes 1/2, and that's the end of the proof. Okay, so in that kind of a proof, you prove it for all possible values of x. Right? It doesn't matter whether x is an integer or real number or irrational number, it will still work, right? Okay, but what if someone tells me, oh, I can prove this. Okay, so x, I would assume that x equals to 5, okay? When x equals to 5, 5 divided by 2 times 5 is 5 divided by 10, it is 1/2. I'll even do one step more, okay? I'll assume that x is a negative value, -2. So in that case, -2 divided by -2 times, 2 times -2 is -2 divided by -4, and the result of that is also 1/2. End of proof. I'm done. Would you consider that a proof that x divided by 2x is 1/2?
Yes.
No.
A few of, or 2 of.
But what makes you think that the next x is going to work too? And the next one, and the next one.
Just keep doing it.
You just keep doing it. Yeah, exactly. But how big is this circle? Okay, we are going back to the dart throwing approach, right? So I'll keep throwing darts until I hit something that's red that will prove that it is wrong, right? But as long as I'm not hitting something that is red, I have not proven that it is right either. It just has worked for all the test cases that I have thrown at it. It doesn't mean that there's no red dots whatsoever. Okay? That is the problem, okay? Because at this point, we can do traces. We can prove an algorithm will work for certain cases, but not for all cases. Remember when we try to find the maximum of 3 variables, and I incorrectly used the greater than symbol instead of greater than or equal to? There are cases that it won't work, but will your test cases include those particular ones? Because if you can think of all the tricky cases to begin with, then you would have caught the bug to begin with as well. So the problem would not have existed. So it is because when we are coding, we are not aware of certain cases that we do it incorrectly, but because of that, when we test the algorithm, we're also going to miss those particular cases. Until you deploy the program in the field and people actually put in those conditions, then your program will work incorrectly. So that would be bad, right? Okay, so that is why we need to use mathematics, because that's the only way to prove an algorithm is correct for all possible cases. Okay, so that is why we are doing this. This whole slide basically talks about there are two giants in computer science. One is Dijkstra, and the other one is Knuth. They are both really big, important computer scientists in recent history. They wrote a lot of textbooks in computer science, textbooks, a lot of algorithm textbooks, and they're both, respected by, basically all computer scientists. One guy, Dijkstra, suggests that programming or computer science is a field in mathematics, just like calculus or algebra or trigonometry is a subject in mathematics. In other words, this class should not have been offered as CISP. It is just MATH. It's a math class, okay? And you have to pass all the elementary math classes before you even take this class. That's his stand, okay? This is that's what he's saying. The other person, Knuth, who is still teaching at Stanford University, he basically claims that well, maybe if we have good tools to use for programming, then maybe we can extend and have normal people also doing programming, or people who are not basically math majors. Okay.
Who do you agree with?
Sorry?
Who do you agree with?
I think they are basically talking about different types of programming. Okay, so let's think about the different kinds of programming that you can do. Okay, programming your DVR. What is the worst thing that can do when you program your DVR incorrectly? Sorry?
You break the device.
You can. Well, you would hope that you cannot break the device just because you program it incorrectly. No, but when I'm talking about programming a DVR, I'm not talking about programming the firmware of the DVR. I'm talking about programming which program to record.
So you do the wrong.
You might miss the program that you want to record, or record the wrong program, right? Okay, well, that's not the end of the world, okay? To most people. To some people, missing.
Miss the last 5 minutes of the show. But that's like.
Then you just ask a friend, or you just search online, right? These days, it's not a big deal, right? Okay, what if?
Raise what you got.
Sorry?
You raise what you got.
Say again? Oh, you raise what you already have? Okay, that's bad too. Yep.
I've crashed the hard drive, just doing too much on it.
Okay, but that's not from bad programming, though. I mean, the programming should not be able to do anything, that harmful.
It's cheap from AT&T,
Okay.
so.
So let's think about another type of program. Let's think about the algorithm or the program that gets into a pacemaker, that gets put into someone's heart. Okay, if that algorithm has a problem, like finding the maximum heart rate, comparing the historical heart rate over different average windows over the past few minutes, that can be bad, right? I mean, if it finds the maximum to be incorrectly, it can come to the wrong decision and decides to, give the heart a pulse when it's not needed, or not to give a pulse when it is needed. Okay, both will be bad, right? So it depends on how critical the program is, and that determines what type of programmer is suitable for that kind of a job. Am I getting this across? Okay. So that means if you want to just program for entertainment, you can just go to scratch.mit.edu and actually start programming right away. I mean, you don't even have to take this class to write programs in this particular environment, because it really is literally drag and drop. Okay, you drag some blocks, you drop it in place, and then it will do something. You can experiment as you go. Go ahead.
I just kind of, it seems as though Dykstra, if you were to create a job title for what Dykstra is describing, he would ask for a programming diagnostician, I guess you could say, because he would have the full spectrum of how it's built and what he should see on the end, whereas Knuth would actually look for a job title of a programmer. There's no diagnostics involved with it at all.
But even when you're writing just a program without diagnostic, you still have to analyze the problem, sufficiently before you can come up with a solution and to describe that solution in a way that the computer can understand. So even the construction of a computer program requires, analysis. Like, okay, how am I going to look at this, particular problem? Okay, let me just, step all the way back. How do you describe the correct behavior of a program? Let's say we're just talking about the maximum program that we were writing. How do you say, okay, if the output or if the variables coming out of this algorithm fit this particular condition, then the algorithm is working correctly. Okay. How do you describe something is the maximum of two variables? Remember that thing that we talked about? Yeah. Okay. That requires math, right? It requires logic, math, in order to even just to describe the correct behavior of an algorithm. So we can't get away from math in any way or form. It's just a matter of how formal do you want to do it. And ultimately, I really think that there are jobs for programmers who are not as strong in math, and there are jobs for programmers there are jobs that require a strong math background in the programmers. But the problem is, when the economy goes bad, the company has to downsize, certain people will be let go and other people will not be let go because of their skill set. So I want you guys to have the skill set to be kept at a company because you can do more than the other people. Okay? All right, so now we are going to talk about pre and post condition. A precondition is simply what we know before the execution of a particular statement in a program. Now that statement can be the very first statement in the entire algorithm. So that becomes the precondition of an entire algorithm. It is basically saying, can we make, or what are we going to assume before this algorithm starts executing? Okay. The post condition is kind of the other way. A post condition is what we know after the execution of a statement in a program or algorithm. Okay? If that turns out to be the very last statement in an algorithm, that becomes the post condition of an entire algorithm. Am I doing okay so far?
Yes.
So we have precondition that applies to certain statements, but the precondition of the very first statement of an algorithm is the precondition of an entire algorithm. The post condition is what we know after the execution of a statement in the program, but if we apply that to the last statement of an entire algorithm, it becomes the post condition of an entire algorithm. So if we know the precondition of an entire algorithm, and we can figure out the post condition of the entire algorithm, then we can now compare the post condition of the entire algorithm to what it is supposed to be. Okay? If you can somehow say, oh, you know what, the post condition of the entire algorithm is equivalent to the condition that says this algorithm is correct, then you have just proven the entire algorithm is correct. On the other hand, if they do not match, then you know the algorithm is not correct. You don't even have to throw a single test case at the algorithm to find out that it is not correct. Yep.
But if you're saying that the circle is infinitely large, and the conditions that don't meet the algorithm are infinitely sparse,
How do you prove it wrong?
how would you prove that it meets the condition for all cases?
That's exactly why we are going to talk about the other topics. Okay? But you're absolutely right pointing out, that seems kind of difficult, right? Because, there are so many, there's an infinite amount of test cases, and, there are only a very small number of test cases. where the flaw of an algorithm can be exposed. So how can this technique be used to conclude, without even trying a single test case, that an algorithm is correct or incorrect? Okay.
So going back to your algebra problem, how can you, what can you throw at that problem that it doesn't equal 1/2?
Well, since it is 1/2, so I cannot prove it wrong, right? It is true. Okay, in this case, it is true that x divided by 2x is 1/2. Okay, so you cannot prove it wrong by throwing test cases at it. But that's only because we know it is true a priori. We know that before we even talk about this whole thing. Now, if it is something else, you can, if your math professor is asking you to prove a theorem, okay, I'm not gonna waste my brain juice on this. I'll just ask algebra proof. Okay. But I'm looking for something that is not correct, right? A theorem that is not right. Let's see. What am I going to do with that? It would be the same as the algorithm that we talked about to find the maximum of 3 variables. Remember that one? So we can throw a lot of test cases at it and still not find the flaw of it, but it does have a flaw. But if we go through the math process to prove, to figure out what is the post condition of the whole thing, then we would have spotted that the algorithm is actually incorrect. Okay, yep, go ahead.
Can't quite remember, but I think an imaginary number would work.
Yeah, but that's not going to be a good example for this class. Okay, so let's go ahead. Let's just kind of move on. I'll give you some examples, as an exposure. So let's forget about all this stuff here because it's not going to be relevant at this point. So what I'll do is I'm going to take a line. This is line 516 out of really, really, really long program. I do not know what is before this line. I do not know what is after this line. I know what this line is, though. Okay, so let me describe what this line is. So this line, let's start with something that's really, really easy, and it's just x gets a value of 42. Okay, on this particular line. Now the precondition is given to you. So when I say pre 516, that really is saying, okay, this is the precondition of line 516. Now this is very significant because what this is saying is every single time before I am about to execute line 516, this condition has to be true. Okay, let me just say that again. This has nothing to do with traces. This is saying every time I am about to execute line 516, the following condition has to be true. Okay. Now, because I'm not showing you the entire program, I'm not going to tell you why it is what it is. So I'll just describe what it is, which is a completely random kind of BS. Okay. Okay. So let's say this is the precondition of line 516. In other words, this is telling me that every time when I'm about to execute line 516 in this particular program, I know that x is greater than k. I know that y is 125, and I also know that z is less than 1/2 of x. I'm not even telling you what k is. I'm not even telling you what z is. Yep, go ahead.
So the second line here, it's saying that if that is not true, then you don't execute 516?
No, it is. It's not saying that. It is saying that under the normal flow, under the flow of the algorithm itself, whenever it is time to execute line 516, this condition has to be true.
That x gets the value of 42.
Well, then x will get a value of 42. The effect of the statement doesn't change. Okay. But the precondition is just saying, every time I'm about to execute line 516, this condition has to be true. Now, I will show you guys how we get to the precondition later on, but at this point, I'm just saying, okay, don't ask me why we have this particular precondition. It's just because of the rest of the program.
So if it is not true, then it's wrong. That really just
No, it's not that. It's actually the other way around. It is, this is proven that this condition has to be true when we execute line 516.
So it just is true.
It has to be true. Okay? All right. So knowing this is the precondition, can we say something about the post-condition of line 516? Okay. So let's look at the first one. X is greater than k. Can we still say for sure that x is still greater than k after line 516?
No.
Probably not, right? Not for all possible values of k. So we cannot say that anymore. All right, that's something that we have to erase. What about y equals to 125? After
Yeah.
line 516, can we keep that?
Yeah.
Yeah, because that has nothing to do with y, right? Line 516 only changes x, and y equals to 125 has nothing to do with x at all. Yep, go ahead.
If y has been assigned as, say, x plus 2, then wouldn't the value that y holds change?
But only in that statement. This statement has nothing to do with y.
But I mean, if you're updating the value of x and the value of y is based on the value of x, wouldn't it change the value of y?
No, because once it is updated, x and y are independent variables.
Okay.
Okay, so once you update a variable, it is no longer dependent on the other one. Okay, go ahead. Same question? Okay. All right. So what about the other one? What about z is less than x divided by 2? Can we still claim that z is less than x divided by 2?
Yes.
Yes.
Do you know what x was? Do you know what z was? Exactly. So we cannot claim that anymore. This has to go away as well, because we can no longer guarantee that z is less than x divided by 2 once x becomes 42. Are we doing okay so far? Kind of? Okay. But you know what? There's one other thing we can say right at this point. What can we say about x?
42.
X is 42, right after the execution of line 516. So that's what we are talking about, okay? You're presented with the precondition of a line, you are presented with the line itself, then you have to figure out what is the post condition of that line. And that's what we are thinking, that's what we are talking about when we talk about pre and post conditions. Okay? Are we doing okay so far with this example?
Yes.
Okay, excellent. So let's move on to something that's a little bit kind of more interesting. Okay, so this one is a little bit more interesting because it says, x gets x plus 1, okay? Which we have seen a lot already, right? X getting incremented by 1. And the precondition of line 17 is saying, for whatever reason, we just know that x is less than z plus k, and y equals to x divided by 2, and k is greater than w. Okay, that's all we know before line 17 executes. So now, what do we know about the variables after line 17 executes? Okay, so if you apply the logic that we did last time, it would seem that we can't say anything about x anymore. So anything that contains x, we have to get rid of. That's not entirely true. Okay, so let's think about this a little bit. If I know that before line 17, x is less than z plus k, and line 17 is going to increment the value of x by 1, right? Is there a way for me to calculate the value of x before line 17 from the value of x after line 17? I can reverse the operation, right? Because adding 1 can be reversed by subtracting 1. Okay? So that means if I subtract 1 from x after line 17, then I will get back the same value of x before line 17 execute. Is that making any sense? No? Yes? Okay. So what about that value? What do we know about that value? The value of x before line 17 executes. It's less than z plus k. All right. So now we can reestablish the relationship between x, z, and k. And we can do the same thing here. Okay? Because we don't know what x is, but we know that x is now one more than what it was. So that means if I reverse back to the old value of x, because I know that line 17 is just adding 1 to x. So if I subtract 1 from x after line 17, I get back the same value of x before line 17. So I'm just reversing back to that value, and this still has to be hold true. And the other one is just simple because it has nothing to do with x. Are we still doing okay so far with this code here? This one is a little bit more tricky because it's reversible. It has to do with whether an operation is reversible or not. Yep.
So for this section, when it says 17 x gets x plus 1, is that line 17?
Yeah,
or is
it
that
is line
saying
17.
At line 17.
It is basically, this is what line 17 is.
Okay.
Yeah. So when we describe an algorithm, I always have a line number next to a statement. So this is basically just whatever is on line 17. All right. Are there any questions about this? No questions? Let's move on. Okay, let's go ahead and look at conditional statements. Okay, conditional statements can be a little bit tricky, but it's not as tricky as we think it is. Okay. So on line 31, we have the beginning of a conditional statement. In fact, we'll use something that we have seen already. Okay, so we'll say, if x is greater than, well, let's try something simple first. Okay, I'll just try something simple. So we'll say if x equals to 5, then on line 32, we'll say x gets x plus 1. Line 33, else. Line 34, we say x gets x minus 1. And then on line 35, we say and if. Okay, now this time it looks a little bit kind of, okay, and I'll give you what is the precondition of line 31. Precondition of line 31. This time I'm going to throw a wrench into this whole thing, and I'm just saying it is true. Okay, can someone remind me again what is the meaning of a precondition?
That's what I know before the execution of the statement of the program.
Exactly, this is the condition that has to be true before the execution of that particular line. Is true true?
Yes, always.
Always, very good. Does it say anything about any variables? The relationship of the variables? Nothing, right? So what do you think that means? That means no. It means I don't know anything about any variables in this particular program. It's the most general way of describing something that is true. Is true itself. Is that making any sense? It's not specific at all. It's not telling me anything about the variables in this program, but it is true. So that means this particular line can execute, and when it does execute, the precondition is true. So it doesn't say anything about any variables, right? Which is okay, because with a lot of algorithms, we start with something like this. Okay, we make no assumptions of whatsoever about the variables. Okay, so knowing that, post 31 is now a big problem. Okay, because line 31 has 2 ways to proceed. That's not a single way to proceed. It has 2 ways to proceed. So that means I can't really say anything about post 31 because it can go to line 32. It can also go to line 34. So that's why we don't even say that. Okay, we don't say anything about post 31. Instead, what we do is we say what is pre 32 and what is pre 34. In other words, there are 2 ways to proceed from line 31. One way is to move on to line 32 when the condition is true, and one way is to proceed to line 34 when the condition is false. Okay? So that's why in this case we don't say post 31, we just say what is the precondition of the two possible lines that we have to execute following line 31. Yep, go ahead.
Is that even ever possible
To
have a precondition that just says true?
absolutely. Well, I'll give you a realistic example next. Okay, so let's try to figure this one out first. Okay, now the precondition of line 32. The first thing I know is whatever is specified by pre-31 still has to be true, because do I have a chance to change anything between line 31 and line 32?
No.
No, there are no assignment statements whatsoever in between. So whatever is true in line 31 still has to be true as a precondition of line 32. But there's one additional thing I know at this point. The fact that I am about to execute line 32 tells me something.
X gets plus 1.
X equals 1 has to be true, right? So now I can add that fact that x equals 5 has to be true. Now for the same reason, I can say the precondition of line 34 is pre-31, because whatever is true when I was on line 31 still has to be true when I'm about to execute line 34, because there's nothing in between that can change any variables. Okay? But that's one extra thing I also know when I am about to execute line 34, and what is that?
X is not equal to 5.
X does not equal to 5. Okay, so x does not equal to 5. All right, we are getting something. We're getting somewhere. All right, we know what is pre-31. It is true. What do you think about this expression? True and x equals 5. Can I simplify this?
Yes.
How do I simplify it?
QED.
No. Come on. We are just simplifying true and x equals 5. It's just x equals 5. Okay, very good. Now, how can I do something like that? How can I get rid of x and something and just have the other side remaining? Now, to some of you, it will say, you are going through this in your mind and you're saying, it makes sense, okay? It just makes sense to me, it's intuitive. And that's not a bad thing, okay? Understanding this, in an intuitive way is not a bad thing, but neither is it sufficient to say, oh, I'll just kind of put this in my proof, okay? So how do you prove something like that? Okay, so I'm gonna do a little bit of a sidetrack here and say, okay, TAC claims that true and whatever is whatever. Do we have anything similar to this in normal arithmetic algebra? What is that?
0. 0 plus whatever would be whatever.
And in multiplication, we have
1.
1 times whatever is whatever, right? Okay, but in normal arithmetics, it is an axiom. It is given to you. Okay, so we basically have to give you all the axioms to build up the entire algebra system. But in Boolean algebra, this is not. It is given to you, but it's not proven to you. Okay, so let's look at the definition of conjunction. I hope you guys still remember the table of conjunction. Okay, with conjunction we have two sides. Okay, we have x and y, and then we have the entire thing x and y. Okay, x is an independent variable, y is an independent variable, so we have 4 possible combinations. Right? Because you have 2 independent variables. When x is true, y can be true or false. When x is false, y can also be true or false. And that's why we end up with 4 possible combinations. Is that making any sense so far? So now we look at x and y, and that's by definition. Okay, this is how we define conjunction. When true is true is true, true and false is false, false and true is false, and then false and false is false. Okay, very good. Now we say, well, looking at this table here, which is really the definition of conjunction, what does that have anything to do with my claim that true and whatever is whatever, or in this case, to prove that this step is valid? We can do it. What do you think? Well, how about we focus on the first 2 rows of the truth table? This is also called a truth table because it shows you, the values of true and false in a table form. Okay, So this is saying that true and true is true. It's also saying true and false is false. Do you notice any pattern in this?
Or
Just
Y.
just these two rows.
Yeah, the Y is the X and Y.
Exactly. The
That's
Y
true.
and the result match. Whenever X is true, then the Y determines the entire result of the conjunction. Is that in any way related to what we are talking about up there? It matches the pattern, right? Because what we have up here, true and X equals 5, is just having X equals 5 being the condition of Y. So if we can do the simplification down here and say true and Y is Y, then we can do the same simplification here and get rid of true and. Now for those of you who want to relate this to normal arithmetic algebra, true actually acts like a 1 in normal algebra, and the conjunction is kind of like multiplication. They have a close relationship. True is almost like a 1, and the and is almost like a multiplication. So that means false is kind of like a 0, and disjunction is kind of like addition. Okay. All right, so that's okay. So we can do this, and now we can do the other part. 31, like that. And here we have true, and X is different from 5. And then we can simplify it to X is different from 5. Now in this class, I'm not expecting you to do all the simplification, but I am expecting people to be able to kind of reason out things, just spell it out, but you don't have to do the simplifications. Okay. Knowing that pre-32 is X equals 5, is there a way for me to figure out what is post-32? Okay? What do you think? Just add 1, but which side? Right? Because before line 32 executes, right before line 32 executes, I know X has a value of 5. That means right after line 32 executes, I know X has a value of 6. It's inescapable, right? I mean, that has to be the way. Okay, well that seems easy. What about the other one? The other one is not quite as easy because I'm not confirming that X has a particular value, because all I'm saying is X has to be different from 5 before line 34 executes. So what can I conclude after line 34 executes?
X plus 1 has to not be 5.
Yep, exactly. I can reverse the operation, right? Because if line 34 is subtracting 1 from X, and I know that the value of X before line 34 is different from 5, then I know that if I just add 1 to X, I can reverse X back to the value before line 34, and that value is different from 5. So I can reestablish the relationship between X and 5. And those of you who want to do the algebra thing, you can actually just move the plus 1 to the other side. So X is different from 4. Is that making any sense? Okay. But this is not an algebra class, so I'm not going to do the simplification. Okay. Oh, by the way, why do you think algebra, just normal algebra, not even Boolean algebra, is important when you become a programmer or someone who has to deal with programming?
You have to know how that works.
It's linear.
It's linear, okay.
You have to understand what that means, what you're typing.
Because you'll be reading programs written by other people. So you have to know that, oh, this expression really means the same thing as the other expression. That is why algebra is important, because you can then actually look at something, you can look at an expression, and you can actually understand what the expression means. What is it trying to evaluate? Okay, so now we have the post condition of line 32, the post condition of line 34. Let's try to figure out the big guy. What is the post condition of line 35? We have a problem here because this is after it merges, right? Remember how we draw a conditional statement? Okay, so I'm going to go to Inkscape again and draw that picture because I want to relate back to what you are seeing here in text. So we'll go ahead and draw a quick picture. So here's a conditional statement. Using a mouse to draw a picture is not exactly easy. Okay, close enough. And we will label everything. We have x equals 5 here. We have the true branch just by convention on the left-hand side and the false branch by convention on the right-hand side. And we have our statement here. X gets x plus 1 and x gets x minus 1. And at this point, I'm going to label the preconditions. Okay, so we know what is a precondition of where. Okay, so we'll go ahead and say this is our precondition of line 31. In other words, the precondition of line 31 is really saying what do we know at this point. Is that making any sense so far? Kind of? Maybe? Okay, let me just do one little fancy thing here. There we go. There we go. So now I like it to be kind of like transparent to translucent so we can actually see the path. Okay, so pre-31 is basically saying what do we know for sure at that particular spot. Okay, if you think about this as a trail, this is saying, okay, when we are about to get into this part of the trail, this is what we know for sure. Well, unfortunately, in this case, all we know is true is true. Wow, how revealing, right? I mean, but that's okay. That simply says we don't know anything. Now, what if I move this down to here? In other words, I'm here, and I want to say something about what do we know at this point. That becomes our pre-32. So our pre-32, or the precondition of line 32, describes, oops, that's the wrong button, describes what do we know at this point. The x equals 5, exactly. But I'm just labeling using the precondition. I'm not going to label it based on the actual condition. So if I want to label this side here, it becomes the precondition of which
34.
line? 34, that's right, exactly. So in fact, this time I'll just label inside this label here. I'll just put this inside too, just to be consistent. There we go. All right. If I want to label this part here, what is it?
Post of 32.
Post of 32? Exactly. Very good. And then we'll label the other one.
Post 34.
Post 34. Exactly right. And now we have the last one, which is down here. What do you think that is? Just in terms of pre and post. Post 35. Yep, that's post 35. And that's the last one that we have to figure out. Okay, so kind of imagine it like this. Okay, it's just kind of imagine this is an actual trail, and I accidentally moved the other one without duplicating it first. So I'm going to fix that. No, I want to just leave. Fine. Do it that way then. There we go. Okay, so now it's all consistent. Okay, so what you want to do is to imagine that, okay, here we got enough time, we can do this. Remember, this is a hiking trail. So what we are doing is we are going to make a little person who's walking down this trail. You can say that's me, that's Tack, right? Okay. So basically, this is saying, every time Tack is walking down this path here, when he's here, he knows that the only thing he knows is true is true. If he is down here, following the logic of the program, he knows that x is 5. When he is down here, he knows that x is 6. On the other hand, if he finds himself over here, come on, Tack, you can do it. When he's over here, for whatever reason, okay, if the execution makes him follow the other path, when he's over there, he knows one thing, right? He knows that x is different from 4. Okay, x is not 4. Okay, it can be anything else, but it cannot be 4. Is that making any sense? Okay. So now the question is, if he finds himself, if Tack finds himself here, what can he say? Now, you have to remember that Tack has no recollection of how he got there. Okay? He was drunk.
It's crazy now.
He just, you know, while he ate certain types of mushroom, he ends up here. But while he's, you know, under the effect of the mushroom, he's still following the logic. That's the most important part. Okay, I cannot ignore the logic of the program. I just cannot remember how I got here. Okay?
X equals 4 or X is equal to 6.
There you go. Okay, so it is a disjunction. Okay, it's a disjunction because I can end up here from either path. So if I came here through this path, I know, you know, post 32 has to be true. If I came in through here, I know that post 34 has to be true. So that means if I want to label post 35, it is post 32. Nope, I don't need the parentheses. Post 32 or post 35. 4. Sorry, there you go. Okay? Because I could have come here from either path. Now, somebody's going to say, but can we make this statement a little bit stronger and say either or? The answer is no. I cannot say either or in general. Because it is possible that both post 32 and post 34 to be true at the same time. That is the case. That is not the case in this particular. It is the case, right? Because when I'm at post 35 and x has a value of 6, I could have come from either direction.
Not both.
Not both. But x can have a value of 6. It cannot be 4, but it can be 6. But if x is 6, I cannot figure out which way I came from. Okay, so that's why you can only use an or, but not an exclusive or. Because when you use exclusive or, like x exclusive or y, that means the entire thing can be true if and only if one of the two sides is true, but cannot be both true. Are we doing okay so far with this logic here? Okay? So I'm just going to give you another example here, which one, and this one is related to what we have already talked about in the class. So this one, I'll start with line 1. You have seen this many, many times, and you will see this more times in the future as well. But we want to kind of look at this one and say, well, does it look familiar to you?
Yes.
Okay. So if I knew which one is larger and is the maximum already, I don't have to go through this loop, go through this conditional statement, because I would have known which one is the maximum, and I don't need to go through the logic. So that means the precondition of line 1 cannot really say anything, because if I knew the relationship between x and y, I don't have to go through this. Okay. All right. So we go through the same logic here. We say the precondition of line 2 is the precondition of line 1, and x is greater than y, because that is the then branch of the conditional statement. The precondition of line 4 is the precondition of line 1, because I cannot do anything in between. And the condition is false, so x is greater than y has to be false to get to the else branch. Okay. So if I know that, okay, so let's do the simplification here first. The pre-1 is just true, and whatever is whatever. Okay. And we can do the same thing here, just do the simplification. So I'm going to shortcut here a little bit and just say x is less than or equal to y, because it is not the case that x is greater than y, x is less than or equal to y. Yep.
So, I'm a little confused. On pre-4 where it says pre-1 and not x is greater than y, I understand the second part, but pre-1 is that, I know that means true. Is it just a general true? It's not specific to any...
I want to use pre-1 here because, in general, with a conditional statement, when you get to the else branch at the beginning of an else branch, whatever is true before the entire conditional statement still has to be true. So pre-1 here, is because of the structure of the conditional statement. We can do the simplification only because pre-1 in this case is true and not some complicated precondition. Okay. So the pre-1 has to be here because in order to go through the proof, I have to do it one step at a time, and that really is because of the structure of a precondition. The pre-1 still has to be true at this point. Okay, so once we know what is pre-4, what is pre-2, sorry. Once we know what is pre-2, what is post-2? x is greater than y still has to be here because z is not in x is greater than y. But what else do we know now? Z has the same value of x because we just copied the value of x to z.
Would you couldn't just simplify that down to z is greater than y?
Actually, I want, no, because I need to establish the equality.
Oh.
Yeah, that equality is actually important. In this case, we can keep, post line 4 is that x is less than or equal to y and z equals to y. That's the post condition. And post 5 is really the combination. Remember, post 5 is post 2 or post 4. So in this particular case, I will just go ahead and copy and paste the two post conditions. So we copy and paste it here, and then we copy and paste it from here. All right, so now we have the post condition of the entire algorithm. If you focus on this line here, this is the precondition of the entire algorithm, which is basically saying, I'm not making any assumptions before the execution of this algorithm. I'm not telling you how x and y relate before the entire algorithm starts to run. And here we have post 5, and because this is the last line of the entire algorithm, this becomes the post condition of the entire algorithm. In other words, without even knowing what x, y, z were before we even start to execute the algorithm, I know this has to be true when the algorithm is all done. Are we doing okay so far with the meaning of the pre and the post conditions in this case? So now the big question is, if you look at this condition here, is that telling you that z is the maximum of the two variables? In other words, without looking at this algorithm whatsoever, how do you express that z is the maximum of x and y? Okay, so let me rephrase that question. Roll this out of the entire screen. I can do this, with a editor. So the question is, how do you express in a logical expression that z is the maximum of x and y? Yep.
Z is greater than x and z is greater than y?
Okay, well that's a good start. Okay, z is greater than x and z is greater than y. Okay, so that is a good modification, kind of important, but that's not it either, right? Because if x is, okay, let's use a particular example. If x is 2 and y is 3, I can make z a gazillion and it will still work. We need something else. How about this? And z has to equal to x or z equals to y. In other words, the maximum of two values has to be the same as one of them, at least one of them. It can be the same as both if x and y are the same to begin with, but it has to be the same as at least one of them. But it has to be greater than or equal to both. Are we doing okay so far? So now the question is, if this is how we can express the correct result or the intended result of the algorithm, can we establish that this is actually the same as that?
Yes.
Intuitively it is, but can we prove it? Can we go through the step-by-step proofs using Boolean algebra to do this? Okay? So I'll give you the answer. Okay, this is not a Boolean algebra class. I'm not expecting you guys to be able to do it, but I'll go ahead and do it to basically say, yes, we can now prove without a single doubt that this algorithm will work regardless of the values of x and y. So am I answering your question earlier in the class? See, I remember those questions. Which is good. That was a really good question. How can we possibly do something like that? And this is the answer. I did not throw a single test case into the algorithm, and yet I will be able to prove that it will work for all test cases. Okay? So we are running out of time today. I will see you guys on Thursday. So you will get a new homework assignment on Thursday as well.